So I'm Aditya and I'll be taking a class on FEs. So the topic is going to be on the topic is going to be on function equations. So functional equation is going to have something like we'll have a function and we'll have some equation on it, right? So is my voice not clear?
It's clear now.
Okay. Clear? Is it better now? Okay. So we're going to see about functional equations. So in functional equations, we'll like obviously have a function and we'll have some equation on it. So like just quickly, the function, let's define a function quickly. So function is going to have some domain and some range, right? So essentially what the function does is it takes every element from the domain, which is A, and maps it to some element B, which is in the range, which is in the codomain B, right? And this is what the function is. So like in functional equations, you usually have domains and like R, which is the set of all real numbers, or R plus, which is going to be like a set of all positive real numbers, or we have something like integers or natural numbers or stuff like that. Right, and like this will be the so like some normal standard domains are like real numbers, positive real numbers, integers, or natural numbers and stuff like that. So like these are some, and like some these are going like the commonly used domains and codomains. Right, and what we're going to have is like we're going to have some equations on this number. Like so, those are what functional equations are. And we'll be looking at some like standard techniques to solve that problem. So my voice is clear, right? I think so. Is my voice clear?
Yeah.
Okay, fine. So like I'll introduce some like, commonly used terms in functional equations. First there is injectivity. This is like usually quite important. Things. So like the what injectivity means essentially is if so essentially we have that if f of A equal to f of B for some A and B belonging to the domain, then this implies A equal to B. This is what injectivity essentially means. So it's like if we consider the map from the set A to the set B, then we have that each element over here maps to like distinct elements over here. And like no two of these elements are same. Like all of these are different. And this is quite useful because if in the equation we have something like f of something is equal to f of something, we can just ignore that. Right. We can just ignore that and like we'll get something, can get something useful out of it. The next thing we have is surjectivity. Which is that for every y in the codomain, like the right hand side, there exists some x in A, so that f of x equal to y. So like if you have a function from A to B, then for every number over here, we can find some number over here so that it maps to this. This what is. So we have these two things, injectivity and surjectivity. So if the function is injective, then it's necessary that f of A equal to f of B implies A equal to B. The other way is always true, but if we have injectivity, like injectivity is not necessarily true for all functions, but if we have injectivity for some function, then we can do this thing. And surjectivity means we can, for every number in the B, we can find some number in A so that it maps to B. This is surjectivity. So like these are some commonly used things in functional equations. So we'll start with an example. Suppose we have an so what we have here is we have a function from set of real numbers to set of real numbers so that we have this condition. F of x, f of y is equal to f of x whole square plus y minus x into 12. So first, what do you think is the function that satisfies this equation? So like when you start with the case, it's like a good idea to first try to find out which equation will, which function actually satisfies this equation, like so that you have an idea of what you want to show.
F of x equal to x is a solution.
Yeah, f of x equal to x is a solution, and possibly like if you want to guess solution, one thing we can do is like we can try putting linear stuff or polynomial stuff in this, and in this case we can check that f of x equal to x seems to be the only solution. If you like try to put some f of x equal to ax plus b, if you try to put something like this, then we'll get that we must have actually if we have that either f of x equal to x or one more solution is that f of x equal to 0, right? So we have two solutions which seem to work.
Sir, how do we figure this out?
Like we haven't figured this out, we're just guessing at this point what functions might work.
Okay.
So we are just guessing that maybe it's a linear function. And if
Yes.
we try linear function, then we can see that x and 0 work. But like we can't say for sure anything about f, or it's like if it's
Yeah.
polynomial or linear, or we can't say anything about that. We're just trying to guess the solution set at this point. So we have got that the solution set is probably going to be something like this. So we can try to look at ideas like injectivity or something like that, except that this function is not injective. So if we somehow eliminate this function, then we can try, if we assume that f is not always 0, then we can try ideas like injectivity and surjectivity, right? So okay, like we can then try to prove it.
Yeah.
And one common trick of proving injectivities is like this. If you have some expression like uh, something in f of y, let's say, like something like f of y plus something f of y square, and like anything f of y, and we have this equal to y. Like we have every occurrence of y occurs in as some f of y except for y alone. So like we have y isolated in some way. If you have something like this, then we can prove injectivity, right? Like, can you see why this must be true? If you have some expression where every occurrence of y occurs only in an f of y, in something like this form, can someone say why it must be injective? Substituting x equal to 0. Let's see. Okay, yeah, substituting x equal 0 gives useful stuff. So x equal 0 gives that f of x equal to f of 0 square plus y f of 0. Right, is what you get by it. And like this must imply f0, like this would imply that f of 0 is 0, right? Like when you substitute x equal to 0 in this equation, you get this expression. And using here, you can get y equal to f of 0 equal to 0 because you can vary y random. Yeah, so that's one thing you can do. Right? But in general, can you people see why, like, if we have something like this, where you have some expression in f of y is equal to y, then the function must be injective.
We
Can
can
you try to
put
do this?
like y equals to y naught and the left hand side equals, so the right hand side must equal, so y equals to y naught.
Yeah, yeah. So the idea is like if you have something like f of a equal to f of b, then if we substitute over here a and b, then the LHS is the same thing. Is a 1 point and b at 1 point, right? So we must have that a is equal to b. So this is like a very useful trick in proving injectivity. When you have something like the one of the terms like x, y, like we have it alone without any alone, and every other occurrence is involved in some f. Like you have f of y everywhere except at one place where you have only y. When you have such things, then proving injectivity is easy. So this is an idea of proving injectivity. And can you see how we can apply it over here? People see why to apply.
We can do like we know that f0 equals to 0 and try to put uh, y equals to 0 now, and we can get like fx is equal to x fx.
Oh yeah, that works. Yeah. That is So that is one solution we have. Right, so I guess we can. Okay, like, okay, let's say we just change the FP then a bit, so it becomes non-trivial. Okay, let us say we put f of x square inside it. I think it's supposed to be inside. Yeah. So the x is not outside, it's just assume it's inside or anything. And so what you would get is that f of x squared is x f of x. That's correct. And the previous FP, the what you said would have worked, yeah, because when you put y equal to 0, then you get that f of x whole squared is equal to x f of x. So let's just work with this FP where the square is inside. So like, can someone see like how we can try to prove injectivity over here?
And I think we can put y equals to x.
Yeah, so after injectivity, that will give something, right? That will be done. When you put y equal to x over here. Okay, there's also some. Yes, yeah, can someone see how we can prove injectivity over here? Using something like this idea. Yeah, like this is an example problem. I'll do some problems later which you can try for some time. So this like this to made a problem to illustrate this idea.
Sir, maybe we can put x equals to 1 and then we get f of y equals to y times f of 1.
Okay. Now we get that.
So f of 1 is a constant, hence I think that should do.
Yeah, this will work when f of 1 is not 0.
Yes, sir.
Right? Yeah. This will work when f of 1 is not 0. And even in general, even directly in this equation, we can do the same thing. Like, let's fix f of x instead. We have f of x f of y plus x f of x minus f of x. I'll probably write it straight. Yeah. So f of x f of y plus x f of x minus f of x square. Assume divided by whole divided by f of x is y, right? Assuming f of x is not 0. Right? And this is exactly of this form. Everything over here is in terms of every occurrence of y over here is only in terms of f of y. This is a function of f of y, but this is y. So this proves injectivity. Because if f of a equal to f of b, we can just substitute over here and we'll get a equal to b. Is that fine for everyone? Is this idea clear of proving injectivity in this question?
Sir, so our goal here is to prove injectivity.
Yeah, like that's the idea over here. Like to solve this, I feel like I'm trying to prove injectivity and then prove this solve it because injectivity in general is like quite useful in FQs.
Okay.
Can we also substitute like f of like x is equals to y, then we get f of x is equals to f of x square.
Right. We get f of x equal to x square. F of x square. Right. So like this is why like injectivity is useful because if we knew injectivity, we could just smooth the f's right now. Right? Because if you know injectivity, then we know that if f of a equal to f of b, this is the definition of injectivity, right? F of a equal to f of b implies a equal to b. So if we knew injectivity, then we would get x f of x equal to x squared. And so we'd get that f of x equal to x if x is non-zero. Is this clear?
Yeah.
So if we have injectivity, we'll be almost done. Like, and I think you already proved that f of 0 is 0 as well. So if we knew injectivity, we'd be done. And to prove injectivity, what we are essentially noticing is that we can essentially write y only in terms of f of y. If f of x is not 0 for some x,
Why are
then
we
because
not
we can write y as this.
why
Can
are
you
we
repeat?
not considering x is equals to 0?
Wait, can you repeat?
Why are we not considering x is equals to 0?
Yeah, we considered that as well. Yeah. Like we did that in the start, right? Using x equals 0. So this is the previous. So using x equals 0, we got f of 0 equal to 0.
Oh, okay.
Yeah, like, but like, is this part clear to everyone? How we got injectivity?
Yes.
Yeah, so like using this idea, we are able to complete the problem. So the idea over here, which I wanted to say, is that if we have some in this expression, we have some term y which occurs alone and without any, like, all occurrences of y are either in some f of y or they're just alone as y multiplied with something which is unrelated to, like, something like which is not dependent on y, like y f of x. Then we can try to prove injectivity in this fashion by writing y only in terms of f of y so that we get injectivity. So is this idea clear?
Yeah.
Okay, so we'll also give another problem to try. Yeah, so you can try this problem for some time. And like, let me know if you have any ideas on this.
F of 0 is equals to 0 here.
Okay, yeah. So when you substitute y is equal to 0, you get f of 0 equal to 0. So also in general, it's like always useful to substitute x equals 0, y equals 0 and stuff like that. So firstly, what do you think is solution set of this?
X is injective.
Okay, how do you prove that?
Uh, so you can fix some y such that f of y is not equal to 0. And then suppose you take two a and b such that a is not equal to b. Then and f of a is equal to f of b. Then if you divide the LHS by f of y into y, and if you fix y, then you get a equal to b. So which is the conclusion.
Yeah. So assuming that there is some y so that f of y is not 0 and y is not 0, we can write this. So again, this expression only depends on f of x because y is some fixed number and this is this x. So again, we get injectivity over here. If f of y is not 0. And if all f of y's are 0, then that's a simple solution, right? Yeah. I can't hear your voice clearly.
X is equals to y, I guess works again here.
X is equal to y will give you f of x squared f of x is equal to x squared f of x. Right. This doesn't like, so this might suggest like if you replace, might think like one possible fix always like you can try to put this and you get f of t equal to t. But the problem over here is that t may not take all values. Right. This will just show that this is true if t is equal to x square f of t. So like this won't work in like, this will just give you for a special case of such numbers. And you can't say that this will work in general as well.
Oh, okay.
So what we want to do is we want to use injectivity somewhere. Right? So we want f of
Can we substitute x is equal to 1 by y?
yeah. So the idea here is that because we want two f's to match, let's just say we want to make these values match. But the problem is that this is not 1, right? So we just make it 1. We just substitute y equal to 1 by x. So what we get is f of x by x squared is equal to f of 1 by x. We are doing the substitution just so that we can use injectivity, because we have got injectivity and it's a useful thing, right? So just to use injectivity, we are putting y equal to 1 by x and we get this. And now this is true, of course, if x is non-zero. And now we are done, right? Because f is injective. So because f is injective, we are able to remove the f's on the outside and we can say f of x by x square equal to 1 by x, which is f of x equal to x. And we already have shown that f of 0 is 0.
Dear, can you please tell again how we come to know about injectivity? I really couldn't understand that.
Yeah, okay, so kind of in injectivity, what we're trying to do is trying to use the same idea as before. We're trying to write x in terms of f of x. So that's what we have done over here. This expression over here. This is just writing x in terms of f of x. It also includes y, but like we can fix y as some constant. So we have written x in terms of f of x, right? So the point is, if you put in this expression, we put x equal to a and x equal to b, and if we have f of a equal to f of b, then we have that LHS is same for both a and b, right? Because both of them are like depend only on f of x. We have no term like consisting only of x or something other. We only have terms depending on f of x. So the LHS will be the same when you put x equal to a or x equal to b. So this implies RHS will also be same. That is, we'll get a equal to b. This is clear, right?
Oh, okay.
So like this is the one very common idea in proving injectivity. It's like when you can get some variable in terms of only f of it. Yes, you're saying something? Or was somebody speaking? Okay, so is this clear to everyone? What did you do over here? we proved injectivity, and then to somehow use injectivity, we substituted y is equal to 1 by x. Because when we do that, we can get f of something is equal to f of something, which is where injectivity is used. So in this way, we can get that y is equal to, like, f of x equal to x consequently. So like this is general idea of like one common way of proving injectivity. So now let's do another problem.
Sir, repeat again.
I couldn't hear you. What were you saying? What should I repeat? What should I repeat?
Sir, how do you prove the function is injective?
Okay, so
I
is
don't
this clear?
understand.
Is this clear that f of y square f of x upon y f of y is equal to x? Is this clear? How we got this equation? We just taken y f of y onto the other
Yes.
side.
Yes, sir.
So the reason we have done this is we get x on one side, and everything on the left side only depends on f of x. There's no term like f of x plus y or anything like that, right? So when we substitute x equal to a and x equal to b over here, this side won't change, right?
Sir, yes.
This side won't change, so this side can't change as well. So when we put a and b, this side is same for a and b, but this side is one time it's a and one time it's b, right?
Yeah.
So we'll get that a is equal to b. Is this clear to everyone?
Sir, isn't f of x equal to 0 another solution? Because there can be a case in which
Yeah.
every y is mapped to 0.
Yeah, f of x equal to 0 is another solution because we are assuming here that f of y is not equal to 0 for some y. If such a y does not exist, then we get the other solution f of y is equal to 0 for all y. This is one solution, and if this is not the solution, like if you look for other solutions, then we get efficiency.
So here we assumed f of a is equals to f of b, and then we said that the left hand side will be always be the same.
Right. Because it only depends on f of x, right? Y is a constant, and it only depends on f of x. There's nothing else in it. Is this clear? Or is this clear to everyone?
Yeah.
How we got injectivity here? Yeah. Yeah. So this is about like how we can use injectivity. So now let's try this problem now. So you can try this problem for some time and let me know if you have any ideas. Yeah, right. So one thing we can do is we can substitute x equal to 0. So in general in FPs, it's always a good idea to try x equal to 0 or y equal to 0 or both. Like in general, like trying these values so that helps because some expressions get simplified. For example, over here, when you put x equal to 0, this expression just becomes 0 directly. And that is quite useful. And in general, putting stuff like x equal to 0, y equal to 0 and stuff helps because if you have 0, then it becomes like if it's multiplied with something, that term vanishes, right? So it becomes quite useful. So yes, we have that f of 0 equal to f of 0 times lower of 0. So if f of 0 is not 0, then floor f of y is 1. Yeah, also like this function is just the integer function. So like x is floor of x is largest integer at most x. So this means 1 is at most f of y less than 2 for all y. This or f of 0 is equal to 0. So this is what we get when you put x equal to 0. So now what can we tell him?
If we substitute x is equals to 1, then we get f of y is equals to f of 1 uh, into f of y. Give.
Into floor of f of y, right? So like we just get some expression like this. Yeah. We get some expression like this. That's what we get. Yeah. Yeah, but like this doesn't seem to be giving some information directly, right? Like one thing we can do over here is we could try making y equal to 1 so that this stuff get cancelled again. That's one thing we can do. But what one another thing we can try over here is by putting y equal to 0. Like in general, like putting stuff like 0, where some terms vanish is like quite useful because we have lesser terms now. In general, in FPs, like if we try to make some stuff vanish or like some stuff cancel, it's like always a good idea. It's usually a good idea. So when let's try putting y equal to 0, so that this term vanishes again. We get f of 0 is equal to f of x times floor of f of 0. Right?
Yeah.
So what we get essentially is that either f is a constant f is constant or is this clear to everyone how we can get this? We just divide by floor of f of 0, right?
Yeah, but it does not help to solve the whole thing.
Like what we can get from here is that we can get f of 0 equal to 0. Can you see how we can get there?
So for like f of x being a constant, doesn't the constant have to be from 1 to 2?
Yeah, So if f is a constant, then this gives solution set of this form. F of x equal to c, where 1 is at most c, this is that. So this is the solution set you'll get if this is the this will be the solution you're getting. So if f is constant, you are getting the solution set. Actually, this is not the only case, or c equal to 0. Because what we get is c is equal to c floors. So these are the two cases when f can be constant. And otherwise, we get floor f of 0 is 0. So we get f of 0 is 0. Right? So like you essentially shown that f of 0 must be 0. Is this fine for everyone? Is this fine, right, for everyone?
How did you show the F0 case? If 0 equals to 0?
No, we are not done. We are just like saying if this part took it. We have proven that f of 0 is 0 or f of x is a constant. This much is clear,
Yeah,
right?
yeah.
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 Okay, and then let's try the substitution. Someone had suggested of putting x equal to y equal to 1. Right, everybody suggested putting x equal to 1 and y equal to 1. Now the use of this substitution is that these two terms get equal. So again, it's a simplification of the equation. We are again simplifying this equation a bit. So like someone had suggested putting this, and this gives f of y is equal to f of 1 floor of f of y. And again, let's put y equal to 1 so that it becomes simpler and we get this. Right? So we get f of 1 is 0 or is this fine for
Yeah.
everyone? Now suppose f of 1 is 0. Can we see how we can be done then? Suppose f of 1 is 0. What substitution can we do over here in that case?
Y is equals to 1 upon floor of x. The left hand side will become f of, oh, that will be f of 1, sorry.
But that may help, but like there's a simpler substitution. It's like just put x equal to 1. What do you get? Or like just look at this equation.
F of floor x into x is equals to f of x into f of floor x, whole floor x.
That is true, but like it doesn't seem very useful. But like if we have f of 1 equal to 0, this just gives f is constantly 0. Is this clear? Please, like, so we are done with this case, right? So like the general idea in this problem is we're just trying to put like make stuff 0 over here. This is the general idea of this problem, because if you make stuff 0, then stuff cancel, right? So we try to put, we got f of 1 equals 0 or floor f of 1 is 1. If f of 1 is 0, we just try to make stuff cancel again. So we put x equal to 1 and we get f of y is 0. This is like f of y is 0. And in the other case, now so what we're left is with this case, where floor f of 1 is 1. right? So is it clear so far to everyone what we're doing over here?
Yeah.
So the idea essentially is trying to make some stuff equal to 0, which is like useful in general, so that we get simpler expressions.
Now we can try to put y equals to 1.
Okay,
So we can get f of load of x is equal to f of x.
right. We can do that. We get f of floor of x equal to f of- right. We get this. What can we do with this? So floor of x is like always an integer, like it's, and we get essentially some sense I've reduced it to like just integers. You can say like, so like, can you see think of some nice values of x for which this is quite useful?
I think like 1 plus something. So
Can you repeat?
no, my idea is not.
So what are some nice values of x we can put over?
Is f of 0 in this case, or is it given as something else?
I can't hear you properly. Can you repeat?
Is f of 0 taken as 0 in this case, or is it some other value?
We have shown that f of 0 is 0 in this case.
Then I guess we can take some some integer from some real number from 0 to 1.
Right. We'll try to make this expression 0 this time. That is, we take 0 at most x at most. This implies f of x equal to f of 0 equal to 0. So if x is small, like if x is from 0 to 1, then we get f of x equal to 0. Right? So let's go back to this. Now what can we put to it? We've got a lot more terms as 0. What we got is floor x equal to 0.
I think you can substitute y equal to some real number from 0 to 1. You would get
Yeah. That's a nice idea. That's useful because, well, this expression becomes 0. Right. Putting x is not useful because LHS will also become 0, so it doesn't give much. So let's try putting on y.
I think you could scale, you could put y equal to half or something, and then scale x as like 2y or something, and you can extend it to all the integers.
So we can actually do it a bit better as well, right? So let's write it down. Can actually make it go through all real numbers as well.
But I think from the previous number we had proved that if you do it for the integers, we are done, right? Because you can like
Okay,
some
right
real
there. That's also fine. That's also fine. So if 0 is at most y is less than 1, then we have this. And yeah, we can put y equal to half or something like that, and we get f of floor of x can just take any integer value. Y equal to and so now we can be done by just taking even integers. So is this clear to everyone what the idea was here? So the essential idea was we are getting a lot of terms as 0 or like getting a lot of or 1 or something like that. And we just trying to use it as much as possible to make more stuff 0. So because like putting values as 0 simplifies stuff. Because like terms cancel. So the idea is clear to everyone, right? The idea is clear.
Yeah, yeah.
So this was about. So like it's always a good idea to put values like 0 in any problem. Okay, so let's do one more problem now. So this is the problem statement. Yeah. This is. So I think you can try it for some time and then share any ideas. So firstly, what do you think is the solution set for this? What do you think works?
Mm,
I think we should start with y equals to 0
yeah,
and
through the
then prove injectivity. And
yeah, this is what we're getting. F of x is equals to f of x square.
Right. So like this suggests that the
Ah,
solution set is probably going to be f of x equal to x squared.
Yeah.
Maybe f of x equal to x squared. And can you see any other solutions as well? Well,
If x equals to 0,
yeah, f x equal to 0 also. So we so the solution set seems to be x square and 0. So this is f of x squared.
if you prove injectivity, I think we're done. But because if we substitute y equals 0, we get this question.
Yeah, so yeah, if we get injectivity, it will be done. Right. That's, but like the previous method does not work over here. Because if we just try to get y in terms of other stuff, we have terms like x square minus y and f of x plus y, which are not in terms of just f of y. And even for x, same previous tricks we did does not work. And actually, there's one more problem with looking at injectivity. Point is that injectivity is not true, right?
Yeah, injectivity is not true because
Yeah.
it makes sense for rules.
So it's like we have like f of x equal to f of minus x. Like it's not known, but in our solutions, like in the solution that works, f of x is equal to f of minus x. So we can't hope to prove injectivity in any way. Right? We may be able to get some form of injectivity like f of a equal to f of b is equal to f of b implies you could maybe get something like this. Like these are all just maybe we can get something like this. But so far, like we have nothing like this. Like so far, like proving injectivity directly does not help because it's not even true. So like this is one reason why like it's good to look at like the solutions that work because if we just try to prove injectivity over here, we won't get anywhere because it's not even true.
Yeah, clear.
So we have to try, let's try something. Injective, there may be a solution with injective as well, but let's for now let's try something else. So suppose here you want to make some suppose you want to make this expression simpler. Like you want to remove some terms. So what do you think you can do over here to eliminate some terms from this expression?
Put y equals to x squared.
Y is equal to x squared. Okay. So we'll get some expression like this, right? So we get some expression. Like this doesn't seem directly. So like instead of looking at what substitution we can do, like what terms do you think you can make cancel? Like what terms you think you can simplify over here? You're actually trying to put some values substitute over here. What values can you make? Can you try to cancel?
I think we can put y equals to minus f of x.
Yeah, that will make this expression man. Okay, that is also a nice idea. Like we get something similar to this, right? If this was y equal to x squared. Y equal to
Y
minus
equal to minus x squared. If
Oh,
we
right,
put
wait.
y equal to minus fx, yeah.
If you put y equal to minus fx, it's that gives something nice. What that gives is f of 0 plus 4 f of x minus x. So what we can notice is that, yeah,
If we put y equal to x square minus f of x upon 2,
yeah, okay, that's also a solution. So the motivation for the substitution is that we want to make stuff cancel. That's the main idea over here. So let's say you just want to make this stuff equal. Because then we can get just this equal to 0. We just try to make this stuff equal for some value of y. So if we just try to do something like this, we just want to get f of x plus y is equal to x square minus y, right? That is y is equal to x square minus f of x. Wait. So essentially what we're doing is we are just created this substitution, which looks like some random substitution, but the idea over here is that we just want to make some stuff cancel over here. So what this substitution gives is that 4 f of x y is equal to 0. So f of x equal to 0 or f of x equal to square. This is essentially just y equal to 0. This y equal to 0.
But will not be in pointwise trap.
Yeah, we'll wait for next step. We are not done yet. That's a nice detail, like we are not done yet. But firstly, is it clear to everyone why we have done this substitution over here? Why we have put y equal to x square minus f of x? So this is like the cancellation trick where what we try to do is we just try to make some substitution so that terms cancel. For example, we just try to put a substitution of like any substitution so that these two terms get cancelled and that just becomes this substitution. And that gives us something useful. This also works, this idea also works, and we get the same thing again. When you put y equal to minus f of x, it also gives us same thing, that it gives us that these two terms are like opposites of each other. So that's also an idea which works. You can try it as well.
Yeah, but in this case, won't the condition will be valid for y is equals to x square minus fx upon 2 only?
For which condition? This condition.
Yeah, y is equals to.
Yeah, right. So we get f of x equal to 0 or y is equal to 0, where y is this particular number. So we get that f of x equal to 0 or f of x equal to x. So here what we have is like the, what is it, was the pointwise trap. So what we have is only, what all we have is that each number is either 0 or x square. But we can't say that it's always 0 or always x square. It could be something like 0 on some values, x square on some values. Is this clear to you? So we could have something like could have a and b not equal to 0, so that f of a is 0, but f of b is b square. But we want to remove such solutions, right? We don't expect such solutions to work. So we want to remove such solutions. So like the one direct way to try to deal with this is that we just try to substitute this into this and like
We
hope to
can
get a contradiction. Yeah.
say like there exists x naught, like if x naught equals to 0, and
Yeah.
try to get stuffs cancel out. So if y would be like if x square minus y, and say that uh, there is a y such that if x square minus y is x square minus y whole square, and if y can't be x square minus y whole square.
Yeah. So that's what we are going to do. So the point is like when you have to deal with such pointwise traps, we just substitute them into that, right? So as you said, like we can substitute a as x so that this term vanishes. And what we'll get is if f of x, we have such scenario, we can get f of y is equal to f of x square minus y. Right, is what we try to really do. It's actually x is was put as a. And now we want to get in b. So let's just put say y equal to b. Get b square is equal to f of a minus b. And this is not going to be the case, right? Because b square is not 0. So we must have a minus b square is equal to b square. That is like even now we are not done, but like we can just try something like this again. Now we can just take that we get a equal to 2b. So if we have such a scenario, then we must have a equal to 2. And
have
okay,
a f of a minus b.
I can't hear you properly. Can you repeat? I couldn't hear you.
F of a square b, I think.
Oh, right. F of a square. Yeah. A square, a square. So, yeah. Which is, so it's get a square equal to 2b. Right? Because a square is not 0, we can get a square equal to 2b. And now, so like, this is the way we can deal with pointwise test, but we're still not done. But can someone see, like, this can't be the case, right? Because we have infinitely many values of b or infinitely many values of a. And this can't always be. Is this clear? Because for all numbers we have, it's either 0 or x square.
Here, can you re-explain how did you, why did you do fy is equals to f a square minus y?
So we put, this is essentially putting x equal to it. So what we want to do is we want to eliminate this pointwise trap, right? Where you have some values as 0, but some values as b square. So to eliminate them, we just substitute these values. So here I just substituted x equal to it. And I got this.
Okay.
So now we put y equal to b as well, because we want to use that as well, right? We want to use both these conditions, so we just substitute these values. And from this we get that a square equal to b, which can't happen because a and b both take, like one of a or b takes infinitely many values, and this can't hold for infinitely many values. Is this clear?
Yes.
So this is what is like the called the pointwise trap. So where we have like two possibilities for each thing, and to eliminate them, we just substitute both. Assume both possibilities are possible, and we substitute them, and we'll get a contradiction. Okay, so we'll now try one more problem. Just a second. So this is another thing. So we can try this for some time. Yes.
X is equals to 0 reduces some terms.
Right. X equal to 0 simplifies this a lot. It just makes it. So firstly, what do you think is the solution set? It's like usually the first thing we like should try. What is the solution set? Because like solution set may help because like, for example, in the previous problem, if we try to prove injectivity, we can't get any because it's not injective. So to avoid such things, it's always better to like try to guess the solution set in place.
f of x equal to 1 is a solution of it.
But it's not, right? It is. It's not a solution set.
Okay, that is
Like f of x equal to 1, if you substitute, you get 1 is equal to x plus y minus xy plus.
then I didn't see the x graph. That's
Oh, okay. So what else work? What if you put like say, wait just a second, like let's take it, this is the right equation, I think.
X is equals to 1 upon fy maybe.
Wait just a second, I think I used the term out here. Oh yeah, sorry, this is supposed to be a 2. This is supposed to be a 2. We have a 2 value. So yeah, we get. So what do you think a solution set will be? Like let's say we try linear
F
values.
f of x plus 1. Sorry,
Yeah.
f of x plus 1.
Yeah, f is equal to x. So like if we just try linear values like x equal ax plus b, f of x equal to ax plus b, then using that we should be able to get that f of x equal to x plus 1 is a solution. And we'll try to prove that this is the only solution.
We can get injectivity of this.
Yeah, right. So it's again the same trick as I told before. This time we try to write everything in like we try to separate y alone. Okay? And we can write it in this form. This is all only dependent on f of y. This as well only dependent on f of y. Right? This is a constant. And this is just y. This is fine. This is clear to everyone.
So here we let x be the constant.
Yeah, we'll fix x and vary y. So if we'll substitute both values a and b. Like the point to prove injectivity is we want f of a equal to f of b implies a equal to b, right? This is what you want to show.
Yeah.
So what we do over here is like because y is like in some sense isolated, right? Because it always occurs as f of y or it just alone as y. So what we try to do is we try to put y as a and b so that all the occurrence of f of y are the same, but y occurs alone, so it's different over there. And we try to get a contradiction out of that if it's not injective. Is this fine? Like, this is the same idea as we used in those previous two problems. So we get if f of x is not equal to x for some x, f is injective. Is this idea clear? It's the same as what we did in those previous problems as well. This problem, we had an expression like this, where again everything x was written in terms of something of f of x. Again, here we have the same kind of situation. Again, we have y in terms of something of f of y, right? We don't have stuff like f of y plus something or f of y minus something or anything. Is this clear?
Yeah,
So is it clear how we get injectivity if f of x is not equal to x for some x? Like the idea over here is again like you just write y is equal to this, right? This is what you're doing, right? This clear to everyone, right?
Yeah.
And if f of x is always equal to x, we can check it out. It doesn't work. That's something we can check actually. So what you've essentially gotten is this. F is injective or f of x equal to x for all x. But like this is also this you can check doesn't work. The given equation. So we have proven injectivity. Right? Is this fine for everyone? How we have proven injectivity?
Yes.
Yes, so now we want to use injectivity. Can you notice something about this term?
X,
Can
Y,
you,
Talk about action.
can you repeat?
Like if we put y equal to x, like if in x's place we put y and y's place we put
Yeah.
x with the same.
Yes, so it's like symmetric and x and y. Complete
no,
symmetric and x and y. Yeah, so symmetry is another thing which is quite useful. And it's especially useful because though the right hand side is symmetric, left hand side is not symmetric. Right? So this makes it like, quite useful. What we'll do is here we'll first put x and y and then we swap y and x. When you swap y and x, we get those. The same expression.
yeah, so we can swap in the left hand side, the both will be equal, no?
Right. This is what we get. And this is due to symmetry because due to symmetry we swap x and y and stuff in chain. So we've got two values of f that are equal. So what do we do now? We can use injectivity, right?
Yeah, f of x plus y f of x is equals to f of y plus x f of y.
I'll just simplify it as this: f of x into 1 plus y. And now we can just substitute any particular value of y or x. Like this, let's say y equal to 0. And now we can just substitute this and checking what works. Right? We have proven this. And we can just find the value of f of 0 by substituting into the equation.
We can also do like fx by x plus 1 will be constant because fx by x plus
Right.
1 equals to fy by.
Yes, that also works. We'll have to make a special case when x is equal to -1, but otherwise it works. So the idea in this problem is we use the symmetry in this. Of course, we have to get injectivity and then we use the symmetry in the problem. It's one side is symmetric, the other side is not. So this is like a useful idea in general. But that was the idea for this problem.
So the solution is f of x is equals to x plus 1, right?
Yeah, like I haven't like done all the details yet, but like when we just substitute this back into the given equation, we can prove that f of 0 is 1 or 0. F of 1, we only get f of 0 equal to 1. When we substitute this back into this equation. Like that, I leave. You can try that just. So have there been any doubts in this? So like some ideas I've seen over here is like firstly we have seen injectivity. Injectivity. So in injectivity, one common idea is we try to separate x or y or some term like that and write everything else in terms of f of x. This is the idea in injectivity, and we have this like cancellation trick where we just try to make stuff cancel in some way. So these are like some standard tricks that are useful. And then we have symmetry. So like these are the three tricks I've seen. And that's also another thing about this pointwise graphs where they come sometimes in problems and we have to be careful that we don't like just say that, for example, over here we can just say that either f of x equals 0 for all x or f of x equal to x square for all x. We can't say that. So like this is like pointwise type and we have to deal with it properly, like by substituting the values where they fail. If we assume that it fails and we substitute those values and we can resolve this. Right? Got the point. So this is clear, right? And one more important idea is we first like putting 0. So like we can put x equal to 0, y equal to 0, or make some terms equal to 0, or if f was surjective, then we can also try to make f of x equal to 0 if f is surjective.
Can you please explain why we only put fx equal to x plus 1, why not, and not anything else?
Where? Like in this part. After this, like I haven't done those details yet. Like what we have shown over here is that f of x is equal to cx plus 1 for some c, right? Is this clear? Or is this clear? So somebody will ask, is it clear to you?
Yes.
Yeah, so what we like we can just substitute over here. Okay, let's do those details. I think like what we'll get is something like cx plus 1 into y plus 1 plus 1 is equal to x, y plus 1 into c is equal to c. C y into x plus 1 plus xy, or actually minus xy. And this must always be true. Right. So here, yeah, we can actually just put x equal to y equal to 0, for example. And we get c square plus 1 equal to 2. And like we can just compare it term wise. What's the coefficient of xy? It's c square is equal to 2c minus 1. Yeah, this actually is better. So when we look at the coefficient of xy, this is what we get, right?
Yes.
Which is just c minus 1 whole square equal to 1. 0, sorry. Yeah, 0. So we get c equal to 1. Or like at this point, like you can have probably multiple solutions. Like you can put some specific values of x and y and we can get the correct. If c is not, you can prove that c equal to 1.
Oh, okay. Thank you.
So is there any other doubts with any of the problems or any of these ideas? Or like why we are doing one, like the idea behind this?
For injectivity, you can use isolation to prove if a function is injective or not. But,
So that's
what are
one
some
way.
other yeah, that's one way. But what are some other tricks to prove that if f is surjective? So if it's
F is
surjectivity,
subjective. F is subjective can also be done in a similar fashion. Right. Let's assume we are in real numbers and we have f of dot is equal to, let's say, y plus something. And this contains no y term, for example. Then this is a way we can deal with subjectivity. Like we just vary by, and this thing varies over all numbers. But this thing does not. This is like the one like common way to do it. And one more way to do it is like when you get f of something like f of y is equal to y or something like that. Like if you have these are called involutions, and if you have such terms, then you can get subjectivity equal to.
okay.
Are there any other doubts in these ideas or any problems you have done something? Are there any other doubts or is it clear to everyone? Clear to everyone? It's clear. That's all I guess I'll stop.